So now this video discusses about what occurs as the circular motion, where we'll be looking at the definition of the circular motion. We should be able to understand what is a circular motion in terms of the definition all about. And we also have to understand about the tangential velocity. So if we say tangential velocity, so what is that one? We'll be able to understand this. And I also have to understand about what occurs as the centripetal acceleration. So what is the centripetal acceleration? We can be able to understand that one as well. And I also have to understand about the centripetal force. So we can have to understand about what occurs as the centripetal force. That is centripetal force. Here we have it as the centripetal acceleration. And from there we should also have to understand about the applications of the circular motion, where we'll be looking at the simple pendulum. So you should be able to understand the typical application of the actual circular motion in the simple pendulum. And we should also have to understand about the application on the object executing the actually a flat corner. That is a flat corner executing should be flat and the horizontal corner. So we should be able to understand about the front and the horizontal corner execution, where the object happens to exit the flat corner. And we should also have to understand about the bank, actually load banking, rather should be the load banking. So that will be the final application that we should have to understand about by the end of the video. So we'll be talking about the load banking. So we should have to understand the principles behind the load banking and the typical analysis behind the load banking. So we can have to understand about the circular motion, what is the definition. We should be able to understand what is the tangential velocity, what is centripetal acceleration, what is centripetal force, and the applications of the actually circular motion in what occurs as the simple pendulum, a flat and horizontal corner execution, and also what occurs as the load banking. So make sure you understand the concepts that will be expressed in this video. And for the sake of interest, make sure that you have the full information about the neurons, the second law of motion. Will be in need of the neurons, the second law of motion in the video. And we should also have to talk about the neurons, the third law of motion. It also be necessary at one point in time. And also even the concept of the vector resolution. We'll much in need about that one as well. But otherwise, let's see how we should have to understand about the circular motion. And don't forget to subscribe to the YouTube channel as well as the TikTok page and GB Analytical School of Science you come across. And I should have to actually subscribe to the YouTube channel as a part of the supporting system, and so that my contents should reach as fast as possible. So keep that in mind. So we understand that we have three types of kinematics. We have what occurs as the linear kinematics. And the linear kinematics, it is the study of the motion in a straight line path. And we also have what occurs as the two-dimension kinematics. So what is the two-dimension kinematics? It is the study of the motion of the object in two dimensions. And we also have what occurs as the circular motion. So what is this circular motion? So if we say circular motion, that is the movement of object in a circular path. That is what occurs as the circular motion. It is the movement of object in the circular path. That is what occurs as the circular motion. And you should have to understand that one of the components of the circle is that it must have the common center. Okay, you should have to understand that the circle must have the common center, and also the circle must have the common radius. Should be the common center, and the circle must also have what we call as the common radius. So now if we say a circular motion, that is the movement of object in a circular path. You know, a circle, actually a circular path of a circle with a common center and also a circle with a common radius. You know, a no circle is there with two centers, and it is also very impossible to have the circle, a typical circle with two radii. It's impossible. So the circle in which the object has to move actually through, it has to be a circle with a common center and also the common radius. So a circular motion, it is the movement of object in a circular path. That is what we call as the circular motion. Now let's say we have, this is the actual center, and we have an object that is being tied to a string, which is the massless string. Let's say this is the massless string, a string that we assume that it has no mass. But of course, in a real sense, you know, each and every string must have some mass. But now we should have to understand that we assume that the string, it is a massless string. And let's say the string is of mass given as m, like this. And now for the sake of interest, let me just have to have it at this. That should be at least somewhere. And let's say we have, this is a case. And now, assuming that the object is moving in a circular path, let's say this is a typical circle in which the object is moving through. By the way, I'm poor in drawings, and basically I struggle with the drawings, but you understand me, by the way. Let's say this is a typical circle. Let me just have something good. Let's say the object is moving in a circle. Let's say this is a typical circle. Let's say that is the case. Now it's a perfect circle, as you can see. Let's say the object is moving in a circular path like this. So at one point in time the object will be here, and at some point the object will be here, and also the object will be here, here, all over along the circle. Now whenever an object is moving in a circular path, let's say the circle is of radius given as r. Now whenever an object is moving in a circular path, always it do have what they call as the tangential speed, and which is always tangent to the circle. That's why it is said to be the tangential speed, and which is given as v. And of course some books they call it as vt, representing the tangential actual speed. And now at each and every point, tangential speed changes the direction. Whenever the object is here, tangential speed will go like this. By the way, you should have this. You know, tangential speed will go like this. And whenever the object is here, tangential speed will go like this. And whenever the object is here, tangential speed will go like that. And sort of. In other words, at each and every point, tangential speed changes the direction. So you may tend to wonder what makes the tangential speed to change the direction, and what makes an object to still move in actually a circular path. At each and every point, the object experiences being pulled towards the center. At each and every point, the object experiences being pulled towards the center. And now the change in the direction of the tangential speed corresponds to the object being accelerating towards the center. So at each and every point, the object feels, or the object accelerates towards the center. That's what happens. So whenever the object is moving in a circular path, at each and every point, the object accelerates towards the center. And what is that acceleration? we call it as the centripetal acceleration. And it is always towards the center of the circle. We call it as the centripetal acceleration. We call it as the centripetal acceleration, which is given as ACP. So whenever an object is here, centripetal acceleration, points towards the center. And whenever the object is here, centripetal acceleration feels actually points towards the center. So at each and every point, centripetal acceleration points towards the center. And since the object feels accelerate towards the center, and basically that's why at each and every point, velocity changes the direction. So object here, the tangential speed will go like this. Likewise, object here, it will go like this, because at each and every point, the object feels being pulled towards the center, and hence it accelerates towards the center. And what is that one? That is what we call as the centripetal acceleration. So how can we be able to have the centripetal acceleration of the object moving in a circular path? Now should be the centripetal acceleration is given as ACP, which is equal to the tangential speed, to the power 2 divided by the radius of the circle. So this is the formula for the actual centripetal acceleration, and basically it is given in meters per second square. So this is how we should have to understand about the centripetal acceleration being given as that, where Vd represents the tangential actual speed and radius is given as r. And basically some books they call it as linear speed. So it is given as the speed square divided by the radius. So you can have this or even this are all the same. So tangential speed is the same as the linear speed. So keep that in mind. And wherever there is an acceleration, according to the Newton's second law of motion, there has to be a force responsible. So the force responsible for the actually a tangential acceleration, it is given as FCP, represents it as, it should be the force responsible for the tangential acceleration. It is said to be, I should say, the force responsible for the centripetal acceleration, it is given as the centripetal force, which is given as the mass of the object times the centripetal for actually centripetal acceleration. And this is according to the Newton's second law of motion. And mind you, wherever there is an acceleration, there is a force responsible for that. And of which we understand that the centripetal acceleration is given as, Vd square divided by the radius of the circle. You have that one. So this is the formula we use to have the centripetal force, and it basically is given in newtons. So whenever an object is moving, in a circular path, it do have the actually a tangential velocity, and it also experiences, being put towards the center. That makes it to accelerate towards the center. And what is that acceleration? We call it as the centripetal acceleration. And the force responsible, it is said to be the centripetal force. So let's see how we can have to appreciate the following questions to do with the centripetal acceleration as well as the centripetal force. And now let's say this is the question. A 500-gram rock, we have the mass, which is given as 500 grams, and of which the mass has to be in kgs, which have to convert. And attached to a string is a wood in a horizontal circle, and the constant speed of that is now the tangential speed, which is given as 10 meters per second. Now the length of the string is 2 meters. So what is the length of the string? That one has to be given as the radius. So because the object is rotating horizontally, and which means the circle which is being formed, it is formed from the center of the circle, of which the distance from the center of the circle to where the object is along the circle, it has to be radius, which is given as the length of the string. So that is, so in this case we have the radius given as 2 meters. Mind you, the radius has to be in 2 meters. And now the question says we should have the centripetal acceleration, which is ACP. So how should you have the centripetal acceleration? We have it as Vt square divided by the r. And from there we can be able to have the centripetal force using the formula, that is using the Newton's second law of motion, which says that the centripetal acceleration should be the centripetal force is given as mass times the centripetal acceleration, or have it in newtons. And now let's say this is the question: an object of mass 5 grams. So we have the mass which is given as 5 grams, but of course it has to be in kgs. And that moves in a circle of radius. We have the radius which is given as 10 meters. So what is 80 centimeter acceleration? So we are looking for the centimeter acceleration, and that which is given as Vg divided by the radius. And by the way, we also have the tangential speed, which is given as 5 meters per second, and we should have the centripetal force that you can have now given as the mass times centripetal acceleration. So have that one. So now that we understand how we can calculate the centripetal acceleration as well as the centripetal force, let's now look at the applications of the circular motion. So one of the actual applications is in a simple pendulum, is in what we call as the simple pendulum. How is circular motion applied in the simple pendulum? Let's say we have the system of the simple pendulum. Let's say this is the case, and let's say this is a typical system of the simple pendulum, and we have an object which is being tied to the massless string. Let's say that is the case, and the string makes an angle theta with respect to the vertical axis, like that. And let's say the string is of length given as L. And now assuming that the object is rotating and happens to form let's say form a circle on a horizontal ground. Let's say that is the case. We just have to present it properly. Just have to look. Let's say the actual object is rotating and happens to form a circle horizontally. Let's say something like this. And let's consider the length should be the radius of the circle, given as, let's say, r, and of which this is the center of the circle, like that. And now if we think of having this one, as you can see, what we have, this is the 90-degree angle, like that. Now we can be able to have the length of the string, we can be able to have the radius of the circle, and also we can be able to have the angle in which the string makes with respect to the vertical axis using the trigonometric ratio, that is opposite hypotenuse. So what is that one? So in this case we can use what we call as the sine. So sine theta is equal to radius divided by the length of the string. So this is the relationship that exists among the angle in which the string makes with respect to the horizon, and the length of the string, as well as the radius of the circle. So keep that in mind. What happens is that the object is moving along, let's say, the circle, and I would say, assuming that the object is moving with the tangential, let's say, velocity given as, let's say, Vt, we can be able to have an interest look at what is the force responsible for the actual movement what is the centripetal force, that is the force responsible, we can be able to look at, we can have the several actually calculations of our interest by looking at the object being rotating and form the circle on the horizontal ground. So first thing, let's analyze the forces acting on the system. Now, since the object is being supported by the string, then there is what we call as the tension force in the string given as G. And also let's consider the weight of the object. Let's say the object is of mass m, then its weight will go like this. So this is the weight of the object given as W. And if we think of extending this like this, we just have to put this. Let's say I should have the tension force somewhere here. And let's say this is my tension force like that. Now if we think of extending the weight like that one, so you observe that this angle theta, it was also the same as this angle theta. Let's say that is the case. And from that point, let's think of looking at this case as now a Cartesian plane. What you have to observe is that this is the y-axis and this is now the x-axis. And as you can see, the tension force, it is at an angle theta with respect to the y-axis. Therefore, let's think of resolving the tension force into components. Now we'll have the x component, that will go like that, we'll have it as dx. And we'll have the y component, that will go like that, we'll have it as dy. And of which, using the trigonometric ratios, you should have to observe that the dy will be given as tension force times cos theta. So have t cos theta, we'll have it as that. And the dx will be given as, we'll have it as dx will be given as t sin theta. And this happens because the angle is against the y-axis. So these are the forces acting on the actual object. But now, what is the force responsible for the actual circular motion? So the force responsible, it is the force that is pointing towards the center of the circle, and which is the x component of the tension force. We have it as the tx. And now, as you can see, it means the motion of the object is taking place along x-axis. Therefore, using Newton's second law of motion, the summation of the forces along x are the ones responsible for the circular motion of the object. And what are the forces acting along x? We only have the tx, which should be given as tx is equal to mass times vt squared divided by the radius, where r is the radius of the circle, and vt, it is the tangential velocity in which the object is moving with, as it is moving along the circle like that. And what is dx? We have it as t sin theta, and which is equal to mvt squared divided by the r. And let's say this is equation 1. You can have to keep in mind. And let's go for the forces acting along y-axis. So along y-axis there is no motion, hence the summation of the forces along x, I should say y, is given as L. And what are the forces along y? We have dy that is pointing up. We have it as the dy minus the weight of the object, which is equal to 0. And of which, what is dy? We have it as t cos theta, that which is equal to the weight of the object. And let's say this is equation number 2. And now from that point, we have managed to have actually 2 equations that we need to understand and to have about. We have the first one, which is given as, we have t sin theta which is equal to m VD squared divided by the radius. And of course, and we also have the one which is d cos theta, which is equal to weight of the object. And this is equation number 2. And let's think of generating another equation that is obtained upon dividing the two equations that we have. Now if we have to divide the first equation by the second equation, what we have is the third equation, that is d sin theta is equal, let's say, mvd squared divided by r, and let's say divide by, we have d cos theta, that will be equal to the weight of the object. And now tension forces will cancel, and what is the sine of a cos? We have it as the tan. So have it as the tan theta is equal to mvd squared divided by, radius, weight of the object. So this is the very important formula that you should have to understand. And by the way, you should have to understand that we have it as m VD squared divided by, and what is the weight? We have it as the mg, of which m will cancel. We can have the third equation, that is now to be expressed as, we'll have it as the tan theta is equal to, have it as, should be about the VD squared and divided by rg. And this is actually the third equation, that is, you should have to understand it. Basically, it is used to have always the angle in which the string makes it with respect to the horizon. You can be able to have the angle theta using this actually equation. In case we have the mass of the object, and let's say that is the case, we have the tangential speed and also the radius as well. But even if the mass is not being given, as you can see, this expression has been obtained upon cancelling the mass here and also the mass that we had here. But all in all, that is how you should have to understand it. But of course, if you wish, you can have it as the tan theta is equal mvd squared divided by the radius times the weight. That is okay if you are not interested to simplify that one. So that's how you start to understand about the application of the circular motion in a simple pendulum. So let's appreciate how we can have, and by the way, another actually equation that we should have to understand is the one that we discussed earlier. We understand that the sin theta is equal to the radius of the circle divided by the length of the string, and this is the only equation that can be used to have the length of the string. And in all cases, let's appreciate the following questions about the simple pendulum as an application of the circular motion. So now let's say this is the question. A 0.075 kg, we have the mass, which is 0.075 kg. A toy airplane is tied to the ceiling with a string, and when the airplane's motor is started, it moves with a constant speed, that is Vt, which is 4.47 meters per second. And in a horizontal circle of radius, we have the radius of the circle, which is 1.28 meters. Now the question is that we should have the angle the string makes with the vertical, and we should have the angle theta. And the question B says that we should have the tension force in the string. So how do you think we should have this? So first of all, we should have a diagram that is showing the information in which the question tries to express about. Let's say this is the vertical, actually a line, and let's say this is the string, and this is the object, And now this is the circle being formed horizontal. Let's say that is the case. Let's say this is the circle formed like that, and where this is the radius of the circle like that, and which is given as, I should call it as a R, and this is the angle theta that we are looking for, and of course, and it should be that, and we have the tension force that is going over like that. So that is the tension force that is pointing like that. It is a tension force, by the way. So in that way, so how do you think we should have to understand the criteria behind the question? So in this case, we should have to analyze the forces acting on the system. We have the weight of the object, that is given as the mg, of course, and let's think of extending the weight up, have that one, and let's think of having the Cartesian plane here. We'll have, this is y-axis and this is x-axis. Now the tension force, it is at an angle theta with respect to the vertical, which is theta. Then we should have to resolve, we should have to resolve the tension force in two components, and as you can remember, we'll have the tension force that is we'll have dx that will be given as, that is the tension force sin theta, and of which the tension force along x will be given as, this should be that, and the tension force along y will be given as d cos theta. We'll have it as that, and from there you should have to understand about the force responsible for the actual motion in a actual circle. That is dx is equal to, we said it's given as mv square divided by the r, and of which dx is equal to d sine theta, which is so d sine theta, which is equal to mv square divided by r. So that was given as equation 1. And also, from what you can remember, you should also have to understand about the forces along y-axis. So what are those forces? The summation of the forces along y-axis are given as along y-axis we have dy minus the weight of the object, which is equal to 0. dy is given as d cos theta, which is the weight of the object. So we are looking for the angle theta, but we cannot use this one because we do not have the tension force, and also we do not have the tension force here. Instead, we should have the ratio of the two equations. In other words, we just have to divide the two equations. What we have will be given as, now we'll have it as tan theta, which is equal to, have it as mv square over rmg, that is the weight. Then we have the mass, tangential speed, and we have the radius, and sort of we can be able to have the angle theta using that one. And of course this is the same as tan theta being equal to v square over rg. Since this same will cancel, we can also use this one to have the angle theta. Now upon having the angle theta, we can also have now the tension force, either upon substituting into this equation or substituting into the first equation, whatever the case, but that's how we should have it. The tension force is given in newtons. Bear in mind that the tension, it is the same as the force, so keep that in mind. So on a simple pendulum, there are actually 4 equations you should have understand. Once again, we have what equated as t sin theta, which is equal to mass times centripetal acceleration divided by the radius of the object. Should be radius of the circle. And then we also have t cos theta, which is equal to the weight of the object, which is the same as mg. That is equation 2. If we divide the two equations, we'll have another equation which is given as the tan inverse should be tan theta is equal to Vd square divided by the Rg. This is equation 3. And we also have sin theta, which is equal to the radius of the circle divided by the length of the string. By the way, it should be given as the length of the string divided by the radius of the circle. Is it like that? Is it like that? By the way, we should have the radius at the top. Radius of the circle divided by the length of the string. That is equation 4. These are the very important formulas you should have to understand. And when it comes to the simple pendulum. Now let's see also proceed our discussions by looking at another application, which is flat corner execution. So now this is the case in which the object, let's say a car, is executing the flat corner. And let's say we have, this is a typical flat corner we can have. Let's say this is a flat corner. It is the corner of which it is formed. It is the corner formed. It is the actually corner formed horizontally. That is what we call as the flat corner. Let's say this is a typical flat corner of our interest. You should have to understand. Let's say we have it as that. By the way, just have this. Let me just have to express it in the same way. Let's say this is a typical flat corner like that. And let's say we have an object. Let's say this is an object. Is executing the flat corner. Let's say that is the case. And now for that case, we should have to understand that. Let's analyze the forces acting on the object. Since this is the flat corner, there is a weight of the object which is pointing downwards, which is given as the weight. And that there is what we call as the normal force that act upwards. So the normal force that points upwards, given as the normal force, given as N. Now, as the object is executing the corner, which is the flat corner, always there has to be the friction force that makes the tire not to skid away. Always there has to be a friction force that keeps the tires of the object to be in contact with the ground to avoid the skidding effect. And what is that force? It is said to be the static friction force, which is given as Fs. And that force is the one that tries to keep an object to execute the corner, and it is always point towards the curve of the object, curve of the circle. Mind you, if this is the nature of the circle, I should say if this is the nature of the curve, it means the center of the circle is somewhere this way. So which means the center of the circle, it is about some places here. So if that is the case, then the friction, actually static friction force, it is the one which is making the object to move in a circular path at that point. So which means this is said to be the centripetal force. So the force responsible for the object to execute the corner or to move in a circular path at this point. So you should have to see this one as a Cartesian plane. By the way, this is y-axis, and this is the x-axis. So which means, as it stands here, it means the forces along x are the ones responsible for the motion, but the motion has to be in x-axis, of course, but it has to be actually centripetal, but the motion has to be a circular at this point. So in this case, the summation of the forces along x are the ones responsible for the motion in a circular path, just at this point where the object is executing the corner. And of which you have it as, what is the force responsible? We have it as a static friction force, which is equal to the mass times now Vd square divided by the arc radius, where actually Vd, it is the speed of the object as it is executing the flat corner, like that one. So that's how you start to understand about actually an object executing the flat corner in that way. And of course we understand that the Fs, which is the static friction force, is obtained using, Fs is equal mu s times the normal force. So which means, in order to have the value of the Fs, by the way, Fs is given as mu s times the normal force. Now how should you have the normal force? Normal force will be obtained from the forces along y-axis. Mind you, summation of the forces along y is equal to 0 since there is no motion along y-axis. And what are the forces along y? We have the normal force, which is pointing upwards to the positive, and the weight which is pointing down is equal to 0. So normal force is the same as the weight of the object. So upon having the normal force, we'll have it here, and basically we'll solve for the actual static friction force. We'll put it here. We can be able to calculate whatever we are interested of doing. So we have two equations that are very necessary for the circular motion where the object is executing the flat corner. We have this equation, and we also have this equation. By the way, there are about 3 equations, and also this equation as well. So keep that in mind. So whenever an object is executing the flat corner, the force responsible for the circular path at that point, it is a static friction force, and that is responsible to avoid the skidding of the object, and it is the one that keeps the tires to be still in contact with the ground. So keep that in mind. Let's appreciate some of the questions associated with the object executing the flat corner like that. Now let's say this is the question. When you take your 1900 kg car, so we have the mass of the object, which is 1900 kg, and for a spin you go around a corner of radius. We have the radius of 53 meters with a speed that is tangential speed, which is given as 13 meters per second. Now the mu s has to be given as 0.88. So we should have to calculate the static friction force responsible for the action. How do you think we should have it? And of course we may have an interest to come up with a sketch of the analysis of the forces, but I just have to keep this in mind. Fs is the one responsible for the circular motion of the object, which is Vd square of r. So in this case we are looking for the friction force, and what would be that one? Since we have the mass, we have the tangential speed, and also we have what we call as the radius. We can be able to have the friction force using that case. And let's say this is the question. The radius r of a rotating loom is, we have the radius, which is 4.50 meters, and the speed, that is tangential speed, is given as 12 meters per second. Now what is the value of mu s actually responsible to keep the child pinned against the wall? So how should you have it? So using the principles behind, much as we have the mu s, it means the object is executing the flat corner, of which Fs has to be given as, should be the mass of the object, and times Vd square divided by the radius of the set. And for this case, we understand that what is the Fs? Fs is given as the mu s times the normal force, which is equal to mass times Vd square divided by the radius. And this mu s will be given as, now we'll have the mu s being given as, mass Vd square divided by r, then divided by the normal force, of which this is the same as the mass Vd square divided by r, times the normal force, like that. So which means what we need is to have the normal force. So we should have to understand that according to the principles behind the object executing the flat corner, in all cases the normal force is the same as the weight of the object, of which the weight is given as the mg, and hence we'll have the mu s being given as, now the mu s we'll have it as the mass Vd square divided by r mg, of which m's will cancel. We'll solve for mu a since we have tangential speed, radius, and that of acceleration due to gravity. So that's how we should have to apply that one in that question. And now let's say this is the question. A 1020 kg car, we have the mass of the car, that is 1200 kgs, and it begins to skid when the traveling at, we have the speed, that is the Vt, which is given as 80 kilometers per hour, and of course it has to be in meters per second. You should have to convert it. Along the curve we have the radius of the curve, that is 125 meters. Now the first question says that we should have the centripetal acceleration, which is the ACP, which is given as Vd, actually m Vd square over r. That we can observe that one. And the other question, let's say a question B, says that we should have to calculate the coefficient of friction between the dies as well as the load. So this is a typical, actually a case whereby the object is executing the flat corner, since we have the information about the coefficient, about the friction force sort of. So we are looking for the mu s, which is the coefficient of the static friction force. So that is the one that keeps an object to still being stick to the actually executing the corner without a further skidding. So how should you have it? So bear in mind that Fs, you should have to understand that the Fs is equal to mass times centimeter acceleration, of which the centimeter acceleration has already been obtained. So which means if that is the case, we have the mass, then we are going to have the Fs. So upon having the Fs, we'll use the formula, which is mu s times the normal force. So since we have the Fs, then we can be able to have the mu s if we have the normal force, of which the normal force is the same as the weight of the object. Then we can be able to have that one now. Now let's finish with a very typical application in circular motion, which is said to be the load banking. So load banking, that's when the that's when the corner is raised at some angle with respect to the horizontal surface. Load banking. What is this? So a load banking occurs whenever an object, whenever a curve has been positioned at an angle with respect to the horizontal axis, or with respect to the horizontal surface. That is a load banking. Let's say we have, this is a typical, let's say a banked load, and basically these kind of loads are constructed in the corners around the hill areas. Let's say this is a typical, actually a banked load. Let's say that is the case. Let's say this is a typical banked load. Let's say that is the case, and it is at an angle, let's say theta, with respect to the horizon. Let's say this is the horizontal surface, and this is the banked load. Let's say that is the case, and as you can see, this is the curve of interest. Now it means the center of the curve, it is somewhere there, and this is basically happens whenever the engineers are designing the curve of a load. And let's say we have an object on a banked load. Let's say this is the object. It can be either it is going towards this direction, or can be towards this direction, whichever the way. So let's think of analyzing the forces acting on the actual system, if that is the case. Let's think of analyzing the forces acting on the system, if that is the case. Again, this is an angle theta of our interest. So first thing, using the principle of the analysis of the forces on the ground plane, we have the weight of the object given as W acting like that, and we have the normal force that is going like that, or as the normal force has to be perpendicular to the surface of the object. Let's say that is the case. We have the normal force that is going over like that. And now let's think of, let's say, extending the weight of the object going over like that. Let's say we have something like this, and let's think of having extending the normal force like that. So what is happening is that, actually, like the same way we discussed about the ground plane, this object is on the actually banked load, and it is exerting the force. It is exerting the force down. Despite that, it is exerting the weight down like this, but it is also exerting the force down somewhere like this, and that force, according to the Newton's theory of motion, is exerting the surface of the a banked load is exerting the same force but up. That is the normal force, so should be that. And now let's see, think of, by the way, you should have to understand that, but anyway, let's keep it cool. Let's say we should have to develop the Cartesian plane like this. Let's think of having the Cartesian plane like this. Let's say this is the Cartesian plane. Let's say this is a Cartesian plane. We should have to understand about. And say this is x-axis, and this is the y-axis. According to the geometry, the banked angle theta, it is the same as this angle. As you can see, the normal force is at an angle with respect to the y-axis. Then we need to resolve that into components, where we can have this is actually x component of the normal force, that is nx, and this is the y component of the normal force, which is given as should be ny, like that. So we need to resolve the angle theta into components. Nx will be given as the normal force times sine theta, and ny will be given as the normal force times cos theta. That's how you should have to observe that one. Now, as you can see, the component of the normal force x, it is the one responsible for the execution of the object at this particular curve, because it is the one which is pointing towards the curve. Therefore, it is the force responsible for the circular motion of the object at this particular curve. So for that case, you have to understand that the nx, it is the force along x-axis. So therefore, the summation of the forces along x are the ones responsible for the circular motion of the object. And what are those forces? We have nx, which is given as the mass times vd square over r, where vd, it is the velocity of the object as it is executing the corner itself. And what is nx? We have it as n sin theta, which is equal to mvd square divided by the radius. So this is basically equation 1. And what are the forces acting along y-axis? We have the weight of the object and the ny component of the normal force. So since there's no motion along y-axis, it means we can have something like this also. Summation of the forces along y is equal to 0, and we have the ny minus the weight of the object, which is equal to 0. And what is ny? We have it as n cos theta, which is equal to the weight of the object. This is equation 2. And let's think of having, the ratio of the two equations. We should have to divide the two equations, where we can have the third equation. So what would you say? Now for that case, we will have the third equation, which is expressed upon dividing the first equation by the second equation. We'll have it as n sin theta, which is equal to mvd squared divided by r, and divided by n cos theta, which is equal to the weight of the object. Normal forces will cancel. We'll have it as the tan theta is equal to mvd square over rw. Of course, w, it is the weight that we can just have to have it as the vd square should be vd square of rg. So this is the formula number actually 3. So which means we have 3 actually formulas associated with the load banking, just like the way we discussed about the simple pendulum. We have the first one, which is given as the normal force sin theta is equal to mvd square over r, and we have the other one, which is given as the normal force cos theta is equal to the weight of the object, and we have the other one, which is given as the tan theta is equal, that should be vd square over rg. So these are the very important formulas you have to understand about when it comes to the load banking. So let's see some of the questions associated with the load banking concept. So how should you have them? And now let's say this is the question: at what angle should what equate as bobsleigh? So we are looking for the angle theta, that is the banked angle. 10-bit actually at what angle should be a bobsled 10 be banked. If the sled moving out, we have the VD, which is given as 26 meters per second, and the radius is given as 100 meters. So we are looking for the actually should be the banked angle. That will be calculated using the angle theta. Actually, tan theta is equal, VD square over RG. We'll be able to calculate the angle theta like that. And let's say this is the question. At what angle we are looking for the banked angle? So should a highway be banked for cars traveling at the speed of, we have the VD, which is 100 kilometers per hour. Of course, we should have that in meters per second. You have the radius, which is given as 400 meters. So the banked angle will be given as the tan theta is equal to VD square over RH. We can have that. And let's say this is the question. A 910 kg, that is the mass, that is 910 kg airplane is flying in a circle with a speed of, that is a VT, 370 kilometers per hour. Of course, it has to be in meters per second. You should have to convert that one. And we have the banked angle, which is given as 30 degrees. Now, how do we have the radius of the curve if that is the case? So in this case, what you have to understand is that we have the formula, which is given as the tan theta should be tan theta is equal to what we should have it as VD. That should be that of VD square over RG. And here we have the tangential speed, we have the banked angle, and we can be able to have the radius as well using that formula. So this is how you should have to understand about the circular actually motion and its applications. Thank you, but don't forget to subscribe to my YouTube channel as well as the TikTok page, GB Analytical School of Science. Thank you.